Hi physics students. In this video, we are going to learn a more general equation for the force of gravity. You may remember from our past discussion about types of forces that the force of gravity is an attractive force that occurs between any two objects that have mass. Right now, we don't have any way of calculating the force of gravity that's exerted between everyday objects. We do have one equation, one formula, however. We have a formula that allows us to figure out the force of gravity exerted on an object that is hanging out on the surface of a planet or moon and is feeling that force of gravity from the planet or moon. And of course, we know because of Newton's third law that object would exert the same amount of force on the planet or moon. So the Fg equals mg equation is great for figuring out the force of gravity between a planet / moon and an object, especially if that object's sitting on the surface. This equation will not work in determining the force of gravity between a pencil and an eraser, or the force of gravity between a giraffe and a zebra. It just will not allow us to figure out the force of gravity in that fashion. So this equation is incredibly restrictive. It does not allow us to find the force of gravity in every single scenario. So the goal of this video is to find an equation, a formula, that is more general, that can apply in more circumstances. Before we show you that equation, I want to kind of relate to you an important story for how this equation was developed, because knowing this information, I feel like, is interesting and slightly useful. So our story begins with this gentleman. This gentleman was an astronomer. His name was Johannes Kepler. And Johannes Kepler was very interested in the orbits of planets around the sun. He meticulously figured out the shapes of those orbits by looking at astronomical observations. In the 16th century, he was able to determine that the shapes of the orbits of planets around the sun is elliptical. An ellipse is simply a squashed circle or an oval. It turns out all orbits are technically elliptical. Now, it turns out circles are a special kind of ellipse, so you can have circular orbits, but other orbits look like an oval. They have an elliptical shape. And Kepler was the first person to figure this out. He did not know why the shape of the orbits were elliptical. And so that became a mystery. Why do the orbits of planets, as they move about the sun, take on this elliptical shape? The next person in our story will be the one that would figure it out. You've seen his picture before. This is good old Sir Isaac Newton. So Sir Isaac Newton, or at the time when he was trying to figure this out, he was just simply Isaac Newton. He had not been knighted yet. Isaac Newton, in the 17th century, decided to kind of tackle this and figure out why the shapes of the orbits were elliptical. The first thing he tried to determine, because, he's the guy that came up with the laws of motion, the first thing he tried to determine was, well, what kind of force is keeping those planets in the orbit? Because at the time, nobody knew that the force of gravity was responsible. So it turns out there's a probably fictional story about Newton that is slightly entertaining. He was hanging out underneath an apple tree, and it happened to be one of those afternoons when you can sometimes see the moon. Especially in the late afternoon, it can happen that you can see the moon in the sky even when the sun is still out. So Newton was hanging out underneath an apple tree. He saw the moon, and he was thinking about the elliptical orbit of the moon going around the Earth. And suddenly, boom, an apple hits him on the head. At that moment, he realized the force that caused that apple to fall is probably the same force that is keeping the moon in its orbit. And for the first time, a human realized that the force that causes things to fall is the same force that keeps astronomical objects in orbit. Now, this may not seem like news to you, but at the time, this was revolutionary. And Newton, realizing that the force of gravity was this force, keeping things in their orbits, was going to set about to try to figure out, well, what does this force look like that causes objects to move in an elliptical path? More specifically, what does the formula look like for calculating such a force that keeps objects in their elliptical path? Before I show you the formula he came up with, I want to better illustrate how Newton realized that the force that causes things to fall is the same force that keeps things in their orbits. I'm going to show you a thought experiment that Newton had that really helped solidify the idea in his head. So let's take a look. This is what we call Newton's canon. The idea is this. Imagine a ridiculously tall mountain on the surface of the Earth. A mountain so tall it would dwarf Mount Everest by many times over. So you can see there's this mountain up here. And on top of this mountain, what if we placed a cannon and we fired a projectile, a cannonball, horizontally off of that mountain? If we were to fire the cannonball off that mountain, you kind of get what you expect. Now, it undergoes projectile motion. We're pretty familiar with that now. And the object falls to the surface because the force of gravity is pulling it down. Then Newton thought about the following. What if I keep increasing the launching velocity of this projectile? So let's increase it to 5,200 meters per second. Okay, so notice how it went further. That's not all that interesting. But let's go ahead and maybe increase it to 6,000 meters per second. Okay, once again, we got further. What about 6,500 meters per second? Okay, so the projectile got even further. But what about 7,100 meters per second? The projectile falls as we expect. Keeps falling, 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 keeps falling. Ah, Newton realized if you launch a projectile fast enough, it will be moving so fast in the horizontal direction that even though it's falling, the Earth is curving away from it as it falls. So Newton realized that an orbit is simply a projectile that is in constant free fall. Really, orbiting objects are a special kind of projectile. And that allowed him to make the connection that the force of gravity, which he was pretty familiar with causing objects to fall, is the same force that's causing objects to orbit. As an interesting side note, that is what is going on when astronauts are on the International Space Station and are weightless. They're weightless not because the force of gravity has gone away, because the Earth is still pulling on those astronauts, but they're weightless because they're constantly falling. Because the space station is orbiting the Earth, they're in a constant state of free fall. Okay, back to the discussion about the formula. So now that Newton knew that the force of gravity was responsible for keeping things in their orbits, he set about to try to determine what a mathematical formula would look like that describes a force in which you have an attraction between any two objects with mass and describes a force that causes elliptically shaped orbits. This was a really difficult problem to try to determine what this formula would look like. Newton spent many months trying to determine what this formula could be. And he was a pretty intense individual, so he spent many months not really sleeping, not really eating very much, just constantly thinking about this problem. And in an era in which there were no calculators, we're talking 17th century here, in an era in which there were no calculators and no way of, figuring out arithmetic easily, he had to do all the calculations by hand in an effort to figure out what this formula could be from the information associated with Kepler's elliptical orbits. He finally did figure it out, but he had to actually invent calculus to find out what this formula was. Yes, that's right. He invented calculus to figure out the answer to this question. Well, the good news is we don't necessarily have to talk about calculus right now, though it would be fun to talk about. This is not a calculus-based course. But we do have the formula that resulted from his use of calculus and his many, many hours of contemplating what this could be. And so he found that a force that causes elliptical orbits is described by a formula that looks like this. The force of gravity is equal to the masses of the two objects multiplied by one another, divided by the distance between them squared, multiplied by a constant. And this is what we call the universal law of gravitation, because this formula works all the time for determining what the force of gravity is between any two objects with mass. The r that you see there, be careful. That r is an unfortunate variable symbol. The r actually stands for the distance between the centers of the two objects. You're going to be really tempted to think that that's a radius, but it's not. The r does not stand for radius. The reason why it's r is because in vector mathematics, sometimes an r is used to describe a distance between objects. And actually, it's something called a position vector. But you don't really need to know that. The key is you have to just translate that r into a distance between the centers of two objects. So if you plug in the distance between the centers of two objects in meters, you square it, multiply the masses, divide by that squared distance, and then multiply by the universal gravitation constant, which is found in the front of your reference tables. And the numerical value is 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared. If you multiply that constant by the other things, you will get a force of gravity in newtons. And the forces that the masses exert on each other must be the same size. Why is that? Good. Yes. Newton's third law. When objects interact, they exert the same amount of force on one another. So by using this equation, you figure out how much force they exert on each other. Now, the force of gravity is an attractive force. So whenever you have two objects with mass, they should be pulling on each other. The force of gravity will never be repulsive. It will never push. It will always pull. So I think it would be a good idea to go through an example of how to use this equation. All right, here's our example. So we've got 2.5 kilogram masses, and they're separated by a distance of 0.75 meters. We want to find out how much gravitational force they exert on one another. So to figure this out, we're going to write out our newfound equation, thanks to Newton. All right. Big G times m1 times m2 over r squared. Now we're going to plug in the relevant numbers. All right, everything's plugged in. Now it's just a matter of plugging it into our calculator. Just a quick word of warning. A common mistake for students is forgetting to square the distance in the denominator. So don't forget to square the distance in the future when you're doing this calculation. You should find a pretty small number if you were to plug this into your calculator. The force of gravity's magnitude for how much force each of these masses experience ends up being 2.96 times 10 to the negative 11 newtons. That is an incredibly small amount of force. So when we're talking about everyday objects, the amount of force they exert on one another ends up being incredibly minuscule. But at least now we have a way of figuring out what the size of that force is, thanks to good old Newton. Well, that's all I want to talk about for today. In class, we'll look at another example of using this formula, and then you'll get a chance to work in groups at solving some other problems, once again, using this formula. Well, stay classy.